Hello and welcome! This is going to be our final video in chapter 26, where we are going through, in the statistics modeling our world curriculum, where we have been looking at the chi-square tests. Thus far, we have talked about the chi-square, and let's do the symbols, the chi-square goodness of fit test. We've done the chi-square test of homogeneity. Those were the two previous videos in this series. And then in this video, we're going to be talking about the chi-square test for independence. Now, we have talked about independence as in many different ways throughout this course. We've talked about it in terms of, from the very beginning, in chapter 3, when we started working with contingency tables, we were talking about independence. And back then, we defined it as, does this proportion, right, of the people in this one match this proportion, or do all three of these proportions match there, or vice versa with the rows? Okay, that was one way that we talked about independence. And we also looked at independence as defined in probability, which is that does the probability of event A equal the probability of event A given B? Does knowledge about event B affect the probability of A? Because if knowledge of event B happening changes the probability of A, it means that those two events are linked somehow. Therefore, they are dependent on one another. However, if knowledge of event B has no impact on the probability of A, then those things are independent, because that means that B does not have an effect on it. Now, the question that I get the most from students when we're talking about independence early on in the course is, well, what if event A was 0.47 and the probability of event A given B was 0.48? Are those independent? And the hard thing to answer in those times back then is that, well, you know, sometimes they're really close and they might be independent, and, you know, how far away exactly do they have to be in order for something to be independent? And we were kind of wishy-washy about that definition, mostly because we didn't have a sophisticated way to explain those differences. And so what we finally get to do in this chapter, thanks to the glory that is the p-value, right? We can tell you that whether or not two numbers are close enough together to be considered independent. Because the p-value, as you will recall, says, given that the null hypothesis is true, what's the probability that we would see this particular sample or one more extreme than that? And what that allows us to do here is we make a null hypothesis that says these two things are independent, and then we check out the probability that we would see these two values being together. And if it's a really high probability, then the likely is that they're independent. But if it's a really low probability, like below 0.05, then they're probably not independent. We would reject the null hypothesis. So because of our sophisticated knowledge now of the p-value, we can really give more evidence as to whether or not some things are independent. So that's exciting, right? We're finally kind of going to get some closure on independence, okay? So again, this is very similar to the chi-square test of homogeneity. We need two variables, right? There's two variables in the contingency table. We're going to see if they're independent of each other. The thing about it is that the test for independence is almost exactly the same as the test for homogeneity, right? The only difference between these two tests, homogeneity and independence, is what you think, meaning what's the approach of the problem? How are we setting the hypothesis? Everything about these two tests are exactly the same, though. It's the same assumptions and conditions. We need enough counts so that the expected values are at least 5 in each cell. So that's something that has to happen. Independence is not something that you need to check because that's what we're checking with this test, is to see if the two things are independent, right? We need randomization if we're looking to want to generalize data to some population. Excuse me. So we do need to have that randomness and sample size as our assumptions and conditions as before. So let's just jump into a problem. Excuse me. So below, meaning in the bottom right here, is a table that shows eye color versus handedness. We did similar examples back when we did chapter 3. Okay. In this case, we have one group of responders who answered questions about two different categorical variables. The question is there an association? Is there an association between handedness and eye color? So does the fact that you are left-handed mean that you are more likely to have blue eyes or brown eyes or some other type of eyes, like green or hazel or something like that, okay? Or is the fact that you have right-handed mean that you're more likely to have brown eyes? That's what we're checking here. So first of all, what kind of test is this? Is it a test for homogeneity or a test for independence? Obviously, this is a test for independence because that's what we're trying out. But how do I know that? Read the question. Is there an association between handedness and eye color? Right? That right there is what's telling us that this is a test of independence. Because when we did tests for homogeneity, the question was, is the handedness or is the eye color the same distribution no matter your handedness? Or I don't remember what I just said. Is your handedness the same for each eye color distribution, or is your eye color the same for each handedness distribution? It wasn't asking if there's an association between them. It was asking if it's the same for each one, which are very similar questions. I totally admit to that, but they are different. Oops, I don't want highlighter. So this is a test for independence. So what does our hypothesis look like? Remember, the hypothesis says that we are going to assume that there is independence, and then we're going to look to see if there's not independence. Now, you have to be careful about how you write this, depending on the vocabulary you choose. Because is there an association? If there is an association, it means it's dependent. If there is not an association, it means that they are independent. So when you write your null hypothesis, you need to write that it's independent. So you can write it one of two ways. You can write it this way, where we say is, excuse me, not is, we're not writing a question, where we would say handedness and eye color are independent of each other. Now, handedness and eye color are independent of each other. That is saying that they are independent. However, if we were using this language of association, we're saying handedness and eye color have no association. Right? So just be careful. I know we're very used to writing our null hypothesis as a statement of equality. The statement of equality is that they are independent of each other. But if we're stating that in the terms of association, it means that handedness and eye color have no association. And then your alternative hypothesis then is just the opposite of that. Handedness and eye color are not independent And then again, if you wanted to use the language about association, you would be saying handedness. Oh, we're getting too close to the bottom here. Handed. Nope. Yep. See, doesn't like it. Doesn't like it at all. Okay. Let's try again. Handedness. Nope, I'm not going to do it. I'm going to write it over here. Handedness and eye color are associated. So remember, this is the alternative hypothesis version of this. I just had to write it up here. So depending on the phrasing that you want to use, you just got to be very careful of how you write that null hypothesis. The null hypothesis is a statement that they are independent, which means they have no association. If they are, and then your alternative then is the statement that says they are not independent, which means they have an association. Okay? Just be careful with your vocabulary. Okay, so there's the big H, right? The big H, the and hammock. Let's talk about conditions. Let's see here. It doesn't say anything about this one being random. It probably should, but we don't need randomness if we want to talk about it in terms of a large population. So we will go ahead and just say here that we're not going to worry. We're not going to worry about randomness on this one. We do need to check the expected values for all of these. So remember, that's going to be the same way that we did it in the previous. To find this particular one, we go 19 times 42 divided by 114. 19 times 42 divided by 114. Okay. To find this one, it's 95 times 42 divided by 114. You do need to know that formula just like you did in the homogeneity. Again, your calculator is super fancy and it will create this expected one for you. I can tell you, after doing it, you get 7, 35, 5.5, 6.5, and 32.5. So there is at least 5 counts expected in each cell. Therefore, the sample size is large enough. And then, since all of the assumptions and conditions match, I'm going to write a statement that says conditions have been met. To perform a chi-square test of independence. So that's the big A in our hammock our acronym. Let's move on to mechanics. The mechanics are identical to the test for homogeneity. So let's go ahead and back out of this show here and take a look at our calculadora. I need to create a matrix in my calculator. So I'm going to go ahead and go into matrix. Now you might notice that there's already a matrix in here. This is from a different problem. You're going to edit it. When you create this matrix A, you do not need to recreate B. So I'll show you that when it comes up. So this is a 3 by 2 matrix. Remember, it's rows by columns. This is 6, 36, 7, 26, 6, and 33. Okay. So that's my matrix. Hit second quit to get out of there. Again, remember, my matrix that I just created for the observed values is an A. This was a one from a different problem, but I don't need to change it. I have to have a second matrix that gives me the expected values for each cell, But your calculator, when you run the chi-square test, just creates it for you, and it overwrites what was in that previous matrix. So this is a chi-square test. Remember, the chi-square Goff test is only for a single variable goodness of fit test. We want, for homogeneity and for independence, we want chi-square test. Our observed values are an A, expected to B, white B in quotation marks, because remember. But when I hit calculate, what it just did, so that's there. Let's just check this real quick. Notice that it overwrote what was in matrix B before. Okay, so it will overwrite whatever it is. There's actually no need to create a second matrix, because whatever you put in matrix B, when you go to run the chi-square test, your calculator is just going to overwrite it anyway. So even if you put the wrong values in B, it's going to take whatever was in A, put the right values in for that anyway. So don't even bother making a second matrix of the expected values, because your calculator just does it itself, because it thinks you're human and stupid. So, okay, so here's my information. My chi-square statistic is 0.708. My p-value is 0.701. It has a degrees of freedom of 2. We didn't explicitly state this, but the degrees of freedom for this test are exactly the same as the degrees of freedom for the test of homogeneity. And I'll write down that formula when we get in there. So let's go back onto our slideshow now, since we have that information. So test is identical. My chi-square statistic was 0.708. My p-value was 0.701, and my degrees of freedom was 2. And so just as a reminder, degrees of freedom is row minus 1 times column minus 1. So we have 3 rows, so that's 3 minus 1 times 2 columns, 2 minus 1. So that's 2 times 1, which is obviously 2. Okay. So there's my mechanics. That's the big M in my hammock step. And finally, let's talk about our conclusion. Our conclusion is based on our p-value. Remember, the same thing applies here. We take our craps. We talk about context. We reject or fail to reject. We assume significance level, and we state our p-value. So my conclusion for this is going to read as, based on a p-value of 0.701, we fail to reject the null hypothesis at the 0.05 alpha level. So that takes care of my reject or fail to reject, my assumed significance, and my state my p-value. Let's make sure we give a sentence about context now. And the context here is, there is not significant evidence, or we could just say not evidence, that handedness and eye color are independent. And that is that. So that would be the end of what we got in chapter 26 in terms of our things. Let's just really quickly, we talked about examining the residuals in a goodness of fit test. It does benefit you to check them in all of the chi-square tests, just the same as we did with the goodness of fit. We can do it the exact same way. Check your residuals. You got to do some fancy calculator work to make that happen. You also got to know about some linear algebra things. So I would suggest you just do those by hand for each cell. But you can see what's really causing it. Finally, we just want to say here that they're really common tests, especially for independence, very widely used. But we do have to remember what this really tells us. The p-value is not proof of causation. And that's one of like the key factors here is that we haven't learned anything like that proves a cause and effect relationship. We've just learned that, for example, with independence, that it's not independent, or that it is independent, or we have evidence to suggest that it is independent or is not independent. Okay, there's different things that you have to do to be able to prove that causation exists. All right. All right, so that's everything that we have for chapter 26. Thanks you guys for watching. If you have questions, comments, or concerns, go ahead and leave those in the comments below. Thank you very much.